Hello everyone, George here, and in this video we're going to take a look at something I thought was kind of interesting. I'm in the middle of having to throw together a last minute kind of demo for a bunch of students coming from the township of Bridgeton from a physics class, and as a reward for getting an A in physics during their high school year, they get to come and visit Rowan University and see all kinds of stuff. I've been asked by one of my coworkers to try to put something together that has to do with physics. So what we're going to see in these next couple of videos is, well, the results of me just playing around and seeing what kind of a demonstration I can put together inside of our 10-sided cave system to show off physics and get these kids more interested in science and mathematics and, you know, the whole STEAM thing, or STEM if you take the arts out. So why don't we just go ahead and see what I've created so far. Let's hit run. This is a very simple simulation, but the entire idea is that we've got a series of different particles. All of them are, oh, that's a lot of collisions right there. But the idea is that they are all being acted on by the gravity of the other particles in the scene. And they are being drawn every fixed update towards one another. And then in order to keep the calculations down, I have them merge into one object when they collide with each other. And that's just to keep this list small. As this list grows in size, especially during the beginning when there's lots of particles all over the place, can't see much. Also, you'll notice the particles are squared or boxes instead of being spheres, and that's just so you can see the rotation and the spin on things after they collide to kind of see what happened. Anyway, why don't we do some more particles than that? So what do we got right now? 35 or so. Let's take that entire list and duplicate it again and just kind of create another group and maybe move it off to the side. And I'm going to take my game window and just move that somewhere out of the way so we don't lose it while I hit run. All right, and here you can see the simulation seems to be running pretty well still. Whoa. Oh yeah, they're all smashing into each other. But you can see once you get past that initial sort of grouping of objects turning into larger ones, you get some pretty fun chaos going on where everything begins to continue to flee away based on their combined velocities outwards, but then gravity, of course, is going to pull all of these guys back into place, and they're all going to come colliding back in. But once again, that velocity is going to increase as they're moving towards each other, and they're going to get flung out again, and you get some kind of cool orbits going on. And it's just a fun demonstration of how you can easily program something inside of Unity. And let's start a new project and do this for ourselves instead of watching this demonstration going on. So let's go to File, and let's go to New Project, and let's call this Gravity. Let's not do the exclamation mark after all. Let's store this on my speed drive. Yeah, we'll do that. I think everything else is good. Let's go ahead and create that project. We're not going to save. All right, new project, new world, new beginnings. So let's go ahead and start with a few things. This entire system is going to work, at least the way I've made it, using two different things. There's going to be gravity objects, which are any object that has gravity and will be attracted by other objects that also have gravity. And then there's a gravity manager. And the gravity manager is mainly responsible for iterating over all the gravity objects, doing calculations to apply forces to them based upon all the other gravity objects in the scene, and then have them slowly move towards each other based on a fixed update loop. So the first thing we need to do is go to Game Object, 3D Object, and let's create a cube. Once again, I'm using cubes just because with a cube you get to see it spin. With a sphere, unless you select this thing in Unity and get a gizmo on it that shows you how it's rotating, you're not going to get to see any of the cool action that happens when these things collide. So we've got our cube. Let's call this a particle, and let's go ahead and just make a prefab out of that, dragging it into our project hierarchy. Now with our particle, we need to make sure it has a few things. It's already got a box collider, which is fine. The next thing we want it to have, though, is a rigid body. Now the rigid body is going to allow us to apply forces to this object and work with the internal physics engine of Unity. This is going to make our life a lot easier. We're also going to want to use gravity off, because by default, use gravity inside of Unity is just a global value that pushes everything down in a specific direction. That direction by default is going to be in the negative y direction, and it's going to be 9.8 whatever meters per second or whatever for objects falling on Earth. But we're not dealing with Earth, we're dealing with objects suspended in space, which means we don't want a global value moving in one direction, so that's gone. The next thing we want to do is go over to collision detection and change that from discrete to or continuous dynamic. If you take a look at the Unity documentation, you're going to notice that it requires more performance, but it's going to be better on an object that's moving continually and dynamically and possibly quite quickly and needs to interact with other objects at the same time. So it's just better to pick something like that. Once again, once you're done with that, hit apply, and now we get to make our first script. So let's right click, create, go to C# script, and we're going to do a gravity script, and we're also going to right click, create, C# script, and a gravity manager script. For the gravity manager script, we're going to go in here, create a new empty game object, call this gravity manager, grab the gravity manager, attach it to that object. Now we have that script associated with it. It's blank right now, but that's fine. We have our particle. Let's go ahead and grab gravity and assign that to the particle as well. Let's make sure we hit apply again, just to make sure that all of our changes to the prefab are applied globally to all future ones that we have. All right, so now why don't we start coding a little bit? Let's go over to Gravity Manager and double click on that to open it up in Visual Studio. All right, now let's do a quick internet search. I know that's dangerous, but we're going to do it anyway. And we're going to talk about gravity equation between particles. So here's our in general case, which is what we care about, brought to us by nasa.gov, and it shows us the force between two objects, and you'll notice there's a big old letter called G, big G. There's the mass of object 1, the mass of object 2, divided by the distance squared between those two elements. Therefore, we're going to need to know what the mass and mass 2 are. Luckily, inside of Unity, if we go over to our particle, you'll notice that we get to specify a mass, so we can set that up and grab it whenever we need. The next thing we need are the distances between those objects. Well, all objects are just transforms, and transforms mean you're at location X and location Y. If you subtract location X from Y, you'll end up getting a vector between those two, a vector 3, and that is going to give us the distance. Then finally, there's big G, and unfortunately, big G is something that we just don't know. We have to figure this one out. So why don't we go back and figure out what that happens to be? So let's do value of G constant. So here we go. We have our value right here. And unfortunately, it is incredibly small. 6.67408 times 10 to the negative 11th. I mean, if you think about it, a floating point number is not even going to be able to store that in it. We need a double. Even so, if we used a value that small, the objects that are moving around are going to have very little force actually acting over them. It's just too tiny a value. So we're going to kind of fudge this value a bit. We're going to say it's 6.67, but we're going to multiply it by something like maybe 10 to the negative 2 or 10 to the negative 3, just so that we're not sitting here for the next year waiting for particles to slowly have enough force to move them around. All right, so back over with our gravity manager. Now that we know a few things, let's make a constant float, and we'll call this big G. Float, big G, is equal to 0.0067 for now. Something approximate, but way off on orders of magnitude, that's for sure. The next thing we're going to need is the gravity manager is going to iterate over every object in our scene. And it is going to then determine how much one object should attract another object. Therefore, we're going to need to know what all these objects are, and all those objects are going to be our gravity objects in our scene, the ones we just made a script for. Therefore, let's create a list that holds objects of type gravity. We're just going to call these gravity objects for right now. All right, so now in start, why don't we go ahead and craft that list? So let's go ahead and do gravity objects is going to be equal to a new list of type gravity. Now we need to grab all those different objects and shove them into gravity objects. Let's do find objects of type, and the type is going to be gravity. There we are. So what we've done here is we're grabbing all the objects of type gravity. That returns to us an array. Now we're converting that array over to a list. Now there's going to be a difference between this and most Unity projects you're used to because we're dealing with physics, using rigid bodies and so forth to apply forces to an object. We're going to want to work with not update, but instead fixed update. This just makes sure that everyone's in lockstep when we're doing things. It's not based upon a frame rate, it's based on a fixed time step that happens within Unity. To accomplish this, we're going to need a double for loop. The first loop is going to iterate over every gravity object we have in the scene. And then the second loop is going to then look at all the other objects in the scene that we have not yet processed and say, hey, I need to apply my gravity force to that object. So let's start with a for loop. So for int I is equal to 0, I is less than gravity objects, dot count, and then I++. Now, as I mentioned, we're going to do a double for loop, so now let's go ahead and make our second one, and that's going to be another for int j is equal to, now j is not going to be equal to 0. Why is this? Because we're going to try to optimize this a little bit. When we do the force calculation, remember that the force is the force between two different particles, particle 1 and particle 2. Once we've calculated that force, we've already done that calculation not only for the first particle, but also for the second particle. So there's no reason for us to iterate over that second particle again and recalculate it. So we're going to be able to skip ahead and make our lives a lot easier. For int j is equal to I plus 1. Now why is it I plus 1? Think about the first time we do this loop. The first time we do it, we're at the first particle in our world. We want this first particle to figure out its force calculation with the next particle in the world. If j was equal to I, it would be figuring out how gravity affects itself, which doesn't make any sense at all. Therefore, we always have to be one element ahead when we're doing our calculations. Then we're going to do j is less than gravity objects dot count, and then j++. Great. Now, in order for us to be able to work with those gravity objects and actually apply forces to them, we're going to need that gravity object to hold references to the rigid body. That's the thing that's going to do all of our calculations for us internally. So coming back over to Unity, let's open up our gravity script and start working with that. So let's go ahead and do a public rigid body, and you might be asking me why I'm doing this, depending upon your version of Unity. Older versions of Unity automatically grab the rigid body for you and created a reference. The current versions of Unity, and probably those in the future, don't do this. Therefore, we have to create the reference ourselves. So we're going to do that by going into void awake. Remember, awake happens before start. It's a great place for us to initialize things. And we're going to do rigid body is going to be equal to get component rigid body. Now that we have access to that, that's great, we can work with it. You'll notice that we have made this value public so it's easy to access for others, specifically easy to access for our gravity manager. Now we also just want to make sure a few things are set up automatically. We want to do rigid body dot use gravity is equal to false. I know we already turned that off, but in the future you never know what kind of objects you might add. It's just a good idea to just do that in code so you're set. We're also going to do rigid body dot collision detection mode is going to be equal to collision detection mode dot continuous dynamic, once again so that we're getting very accurate calculations for a system of continually moving objects. With that, we've pretty much set up our gravity object. I know it doesn't look like much now, but when we add additional features in future videos, it's going to become a little bit more robust in sections like on collision enter and so forth. And if we add sound or possibly the material changing based upon collisions, all that's going to go inside of this spot. For now, let's jump back into Gravity Manager and make some more changes. So now that we've got our loops iterating over everything, we can start figuring out the force calculations between different objects. So the first thing we're going to do is create a vector 3, and this is going to be the force direction. That is the direction the force is going to be applied from our current object to the next object. Let's go ahead and do a vector 3 and force direction. And this one's pretty easy. It's just going to be gravity objects. And then that's going to be the jth one, dot transform dot position. So it's location in space minus the gravity objects I, the one we're currently iterating over, dot transform dot position. Now, hopefully you already know that when you subtract two vectors from each other, if you subtract vector A from vector B, that is A minus B, you're going to get a vector that points from B to A. And that's exactly what we've done here. We need this so that we know the distance between those two different objects, as well as the direction that this force is going to apply on an object. Remember the force calculation we saw earlier. Right here has no vector element. It doesn't have a directionality. That direction we're calculating right now, this is going to provide us with a scalar value, and then we multiply that scalar value by the direction we want this to be applied in, and that's going to be our force. All right, next up, why don't we calculate what this force actually is? So we're going to do float scalar, and we're going to say that's going to be big G, which we of course have up here, times our gravity object's I dot rigid body, which we can now access because we just added that in the previous script, dot mass, times our gravity object's J dot rigid body dot mass. Now that entire quantity, let's put some parentheses around it, is going to get divided by our force direction dot magnitude, which is the distance between the two vectors. And with that, I mean, if you want to, you can put another parenthesis in there just to make it look like the other equation, but based on order of operations with mathematics, it shouldn't really matter. Now let's calculate our actual force that we're going to be dealing with. That is going to be a combination of our force direction and our scalar value. So vector force is going to be equal to our force direction dot normalized. We normalize this because we only care about the directional component. This gives us a vector that has a magnitude of 1, basically. And how big that value is going to be, that is its magnitude, is going to be the scalar value we just calculated. So now we multiply that value of 1 by our scalar. Now all we need to do is add these forces to our two objects that we're working with right now. We're working with gravity object I and gravity object J at the same time. So let's do gravity objects I dot rigid body dot add force, and that's going to be just our force value. It's going to be equal and opposite for the other object. Remember that right now our force direction is going to be pointing from object I in our array to object J. The force for object J, though, is going to be in the exact opposite direction. It's going to be going from it to the other particle. Therefore, we need to flip things around. So now we're going to do gravity objects. I'm going to do J dot rigid body dot add force. And this one is going to be force times a negative 1.0 F. The idea is to flip the vector, the direction of it. Still the same amount, still the same scalar value, it's just pointing in the exact opposite direction, which will be towards the other particle. And with that, we now have a system for having objects attract each other based on fixed update. So why don't we go over to our scene now, check for any errors, not seeing anything right here, keep the game view out of the way because we're going to be watching everything through the scene view at the moment. And let's go ahead and create a couple more particles, and let's do 2 for the beginning. Make sure everything works and see if they attract each other. Now go ahead and hit play. And if we zoom in, let's see if anything's happening. And you'll notice they're moving ever so slowly. Now, why are they moving so slowly? Well, because of 2 different reasons. One of them is because of big G, which is a really small number. Therefore, it's only going to be applying a little bit of force throughout this entire thing. Now, what's another parameter we can change if we want to keep big G at that value? Well, remember, it's also based on the mass of the objects and the distance between them. So as they get closer, the force will get stronger. But for right now, if we take a look at our particles, we're going to notice that we have a mass of 1. 1 is very small. I'm guessing this is, for all intents and purposes with us, 1 kilogram. Therefore, why don't we grab both particles and change that mass to something higher, maybe like 100. Now let's go ahead and hit run and see what happens. We can automatically see that they're starting to move and they're starting to come together. And then they should snap, bink, right there. All right, well, that wasn't very interesting. So why don't we make this a little bit more visual, add some more particles, set them off in different locations, different places, and let's see what happens. I'm just hitting Control D on the keyboard. Let's hit run. So here they are starting to come together, and bing, 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 bing. You can see them constantly trying to be pulled together towards what would be becoming our center of mass. And then eventually they become stable, partly because these are cubes rather than spheres. Although, look, they are moving a little bit here every now and then. We can see what's going on. So why don't we make this a little bit more interesting and continue to increase the number of particles we're dealing with. And we're going to run into a problem once we start hitting, I don't know, say 60, 70, 80, 100 particles. And that is the system just becomes bogged down with computations. So let's go ahead and hit run. And let's see, what do we have right now? We have 24 particles. Let's try 24 and see what happens. So actually, we're doing pretty well. If we go over to our game view and hit stats, we're only 13 milliseconds on the CPU, which is pretty good. Well, we're going to see that it gets a lot worse soon. And then they all kind of clump together. Not a whole lot of interesting dynamics going on yet, but not bad. Why don't we grab all these particles, everything that we've created, and duplicate that again? And instead move that off a little bit to the side. The idea here now is that all these particles over here are going to kind of form one ball, and all these particles over here are going to form another one before they eventually kind of coalesce and create one giant one. So let's go ahead and hit run. Now we're up to 49 of these. We're up to still CPUs doing well. Not too bad at all. Here we can see them coalescing, coming together, and then now they're being pulled to each other, and then bam. And then that's kind of fun. So kind of interesting. Now let's do something really dumb and grab all of them, duplicate them, and move this group up and over somewhere. And I'm just going to grab maybe this entire group and move that off. I'm trying to add some variation in what's actually happening here. So it doesn't really matter. Just try to do something. And let's go ahead and hit run. Now we're up to quite a few of these. CPU still doing well. We're at 99 particles, or 100 particles actually. So you can see them converging there, coming together in the background as well, smashing into each other. And there we got a separation event happening. See, now it's going to get a little bit more interesting. This one has picked up a lot of velocity, and when it smashes into the other one, it's going to break it apart. And we can see that happening. And actually, look how far apart they are right there. And then they're going to converge again. Now the gravity is starting to take, look, down here at this one right here, gravity's finally pretty much overcoming the velocity, the ejection velocity it had, and is going to be coming back towards the other group. But once again, it's going to pick up a lot of speed and momentum as it's doing that, and it's going to smash into something, or it's going to go just zoom right on past, and yeah, going to miss it. So we'll see what happens in a second. Oh, there we go. That was a nice smash event. And then it, of course, reconstitutes itself. It brings everything back together. And now we can see these sort of orbits happening where we're moving around each other. Let's see if this one, is this going to be a smash? Nope. That one's moving out of the way. That one moved out of the way. This one's coming in hard. Nope, going out. Anyway, that's all I have for this video. This is the first and probably at least 2 or 3 more videos on working with this system, and I just thought it was pretty interesting and fun. It's a very easy experiment to put together inside of Unity that anyone can do, as you've seen. Just really takes maybe 10 minutes. But it produces some pretty fun results of a dynamic system moving and interacting, and it's just fun to watch. And I'm sure you'll find some interesting way of using this in your own game or other developments. Anyway, so long everyone, and goodbye. George out.